All yours, yes.
Okay, great. Thank you. Welcome, everyone. It's our great pleasure to welcome you to this ECL AI Center weekly seminar series. And today we're very pleased to welcome Théophile Cantelope from Inria Paris, ENS, and the Inria London program. So I'm obviously not objective because Théophile is actually doing his PhD under my supervision, also with Alessandro Rudi back at Inria Paris, and our own Carlo Ciliberto from the AI Center. So Théophile will be speaking about a recent contribution to this on dissimilarity, discrepancy, and diffeomorphism invariances. So Théophile, the floor is yours. I'm going to mute myself. And as always, if you do have a question or remark, please feel free to raise your hand or mute yourselves, and you're very welcome to ask your questions. Théophile, all yours.
Okay, so you should be able to hear me. We switched to the sound. Thanks for the introduction, Ben. So as Ben said, I'll be talking about measuring dissimilarity with diffeomorphism invariance, which is some recent work we put online. So let's jump right in. Feel free to interrupt if you have any questions. So the setting is the same as I think many of you are very familiar with. Image classification, clustering, retrieval, some standard tasks in machine learning. And in all these tasks, having a distance metric, or a divergence, or in general, a dissimilarity can be quite useful. So for example, here for clustering. And furthermore, in the wild, data can present some form of deformation. So for example, here, these are some images I took in my apartment. So you can see that you can have flowers from 2 points of view. You can have maybe a poster on a wall with a raccoon from 2 points of view. So a perspective transform, a rotation, a translation, things like that. And so what we'd like perhaps is to have a machine learning algorithm that sort of knows about this and can enforce some form of invariance. So what's the problem statement? The idea is to find the distance between images. So for example, images, but it could be more generally data, which is invariant to deformations and computable in practice. And so with this distance, we can then use it in different machine learning algorithms like nearest neighbors or clustering, etc. And so, for example, if we had, some rectangles, rotated rectangles, some squares, and on the other side, some ovals, some circles, some ellipses, you can see that both of these groups are sort of diffeomorphic one to the other. There's deformations that transform them one into the other. And so when we have a new data point like this, form, where do we want to put it? So first, let's restrict ourselves to be reasonable and for everything to make sense. We're not going to look at any type of deformation, which would be any type of function. Here, we're going to look at smooth diffeomorphisms, so functions that are continuously differentiable and bijective. And the idea is to enforce an inductive bias, which is that we want data that is a diffeomorphic transformation of another piece of data to be close in according to this distance that we're going to build together. So for example, here, we'd want it to go with the yellow group because it's diffeomorphic to this group. So I talked about, I said the word inductive bias. So I know this isn't something that's necessarily very fashionable, but the fact is that labeled data is expensive. Behind every data set with 1 million samples, there's many people who have been paid not very well, even though it's expensive for us. Data augmentation is also expensive. And so more data means more compute time, more training time. And in the past, and more recently, enforcing inductive biases has shown promise. For example, people developed invariant kernels and are returning to them. Also, others have shown, including people from UCL, that enforcing convolutional neural network-like structures, so for example, enforcing invariance to translation in simple structures actually yields very good performance on tasks. So this is something that seems to make sense. And so let's jump in. So first I'll introduce sort of the main key idea, which is to see data as a function. to see each datum as a function, each point of data. Then we'll go through sort of an intuitive, informal derivation of the distance, how we got to the definition I'm going to present, and then show some theoretical guarantees that accompany the dissimilarity that I'm presenting, and how to compute it in practice, which is of course of utmost importance, and then finally some demonstrations. So the key insight is to see images as functions. Why? Because if we have an image, so for example, this golf ball that's from ImageNet, and we transform it here using some form of diffeomorphic warping that's randomly generated, we can have this deformation on the space of images, tau, for example. And so there's a lot of ways to parameterize this. And so one way we can try to think about it is seeing an image as a function. And so in that case, for example, we'd have input coordinates that are in R2. So the coordinates of the pixels, for example, and as the output in R3, for example, RGB channels, but it could be another color space or another basis, let's say. And so then how does tau act on this function that takes X and gives us Y? So it's the same thing as a right composition with the diffeomorphism, if we're limiting ourselves to smooth transformations. And so the transformation is bijective, like the one on top. And instead of composing an abstract object that's an image on the left, we're composing the input space. We're applying a diffeomorphism on the input space. So we're transforming the input space, and you can see it as deforming the grid of pixels. And so this is what's done to get the image that's on the right. So this is going to be the key idea. And so deformations are exactly the same thing as a composition, right composition by a diffeomorphism. So let's go back to the...
When you say input space, do you just mean the X, or do you mean the...
Yeah, exactly, the X.
So you don't change colors, anything like that?
Yeah, exactly, okay. Exactly. Yeah, so it's only over, so it looks, the transformations look like this. So the green stays green, the white stays white, but the shapes change in a way that's smooth.
Cool.
So let's go back to what I said was the problem statement, which was to find the distance between, so now it's functions, not necessarily data. So functions, which is invariant to diffeomorphism, and that's computable in practice. So for example, this same object, the golf ball, can be transformed in different ways, warped in different ways. So I didn't show the rotations because it's not very interesting, but here you can see some different sort of warpings of the golf ball. And I zoomed on some images. You can see we have this perspective transform for the raccoon's paw. And also, for example, if we have this object and then a scene in which this object appears, we can want to see if we can sort of build a diffeomorphism. You see that there's a rotation, maybe a perspective and a scale difference. Can we show that these two images are close because the first one is sort of embedded in the second? So this is sort of the problem we're going to be talking about. So let's get into the intuitive and informal derivation of how this distance is built. So the main idea is to use the change of variable formula. So I'm sure you are all familiar with this formula. And so if we know the transformation Q that transforms, let's say, f into another function g, so if g is f composed with q, then integrating allows us to get the same value if we add the Jacobian term, so the absolute value of the Jacobian, the determinant of the absolute value of the determinant of the Jacobian matrix right here, okay, of Q. So the change of variable gets rid of the diffeomorphism. And so integration is an interesting direction to go down. However, in general, we don't know the transformation that is taking place. We could maybe try to regress it if we know that we're looking only at translations and rotations, for example, or rigid body transformations. We can regress it, and there are some techniques to do so using Fourier, for example, techniques, Fourier transforms. But in general, it's unknown, and we want to do something very general that's going to work for a very large class of diffeomorphisms. And so in this case, well, let's be naive. Let's try to regress this value. So if it's unknown, let's try to find it. And so let's call it small q. And so we're going to look for the minimum of the distance between the absolute value, between the integral of g with weight q, so which is supposed to become, so g is f composed with q, big Q. So small q should become, when we minimize it, the absolute value of the Jacobian matrix's determinant, right? So this is what we're trying to find. So what's the problem with this? Well, in general, so of course, the Jacobian term is a solution that yields 0, but there's another solution that yields 0, which is f divided by g, right? So if our output space is nice enough for us to do this operation, we have sort of this trivial solution. And so we'd like to avoid this solution because it's not interesting and it doesn't reflect the transformation that happens between the two images. And so to do so, we can try to go a bit further. So let's think about this. If Q, the quotient between F and G is a match, right? It won't be a match, however, for if we look at F squared and G squared, right? Whereas the Jacobian term is a match. If we apply the change of variable formula to F squared and G squared, for example, coordinate-wise, then the quotient term wouldn't be, let's say, a good solution, but the Jacobian term will still be valid, right? Will still yield 0. And so what we'd like to do is match all the moments, let's call them statistics or moments of the images, F and G. And so these can be, for example, all polynomials of the images. And in general, it'll be all functions from the output space Y to R that are in like a family, let's say V, of elementary functions, right? So this is the third step, sorry. So for example, we can take, as I was saying, the monomials. And so now we've solved the first problem, but we still have another problem, is that what happens if we permute the pixels of an image, right? Because, so for example, we apply a permutation of pixels. Well, a permutation conserves the sum, right? So the integral of two permuted images is going to be the same. And so here the problem is that we're going to say that the distance between them is 0, even though they differ by a very non-smooth, non-diffeomorphic transformation. And so we don't want this. And so we want to exclude big Q if Q is very irregular. And so to do this, so here Q equals 1 achieves the equality, sorry. And so to do this, we're going to add a uniformity on regions. So we're also going to regress on the right side with F here where I'm pointing. And this is akin to highlighting different regions of an image and saying, we want that all the moments of the image match, but on every region we can imagine, okay? So the problem becomes, so before it was a min-max, and now it's a max-min-max. So for all the regions of the image, H, we want to find another region of the image, of the other image of G, such that all the moments of the two images match, okay? And so this gives us uniformity, which allows us to detect a diffeomorphism. So
is each little h like an indicator function over a given region?
Yeah, so it could be. Actually, right now, so what's denoted, the calligraphic h is going to be a nice, well-behaved function space. So it's more like, let's think about it as like a Gaussian, like a smooth weighting. So instead of being an indicator, it's going to be rather smooth. But yes, that's the general idea, is that it's going to highlight regions.
Okay, thanks.
So actually, H1 is going to be the unit ball of an RKHS, but I won't go into too much detail, but that's the general idea. Yeah. So how does this work on a very fake example, as you can see? So let's say we have an elephant and a lion. Well, let's say the elephant is F, the lion is G. So for any region, the max of H, so we're going to choose, for example, these two hind legs. Maybe we match the forward legs, right? There's no obligation to match the hind legs. There's no spatial coherence. If H is the tail of the elephant, maybe it'll match the tail of the lion because the two shapes are quite close. They just differ by sort of scale in a slight deformation. And then if we take, for example, the rear of the elephant, it looks a lot like the rear of the lion. And if we take the head of the elephant, well, you know, it's not quite clear, and it's not necessarily the head of the lion. It could be the rear of the lion, but in any case, we're going to transform it, and it's going to become, right, something with a trunk, with a trunk, sorry, that looks like the tail of the lion. With, you know, so we shouldn't expect too much from it either. But so this is the general idea. So here's a scary formula, which is the formal definition. We have two functions f and g, which are, for example, our images, right? That's how we should think about them. And we have an RKHS over x and an RKHS over y. So function spaces, okay, to think about it simply. And so what are we going to do? We're going to say exactly the same formula as before, the max over h, the min over q, the max over v. And so here you can see that we're taking a function h with a small norm, a function q, and then a function v with a small norm as well from another space. And so the goal is to match the quantity that we built together 2 minutes ago, and we add some regularization. So let's just remind ourselves what each ingredient is. So we have a max over h that applies to the f image, the first image. This is a 4NE, right? A max is a 4NE region on f. Then we have the min over q. So 4NE region on f. We find the region on g, on the other image, such that for all v, the quantities are close. And so which means that we match all the statistics or all the moments of the pixels. And we limit ourselves to using only smooth Jacobian terms because we're going to regularize. So this is just Tikhonov regularization, okay? So that's the formal definition. And so now
what's mu?
Oh yeah, so so let's let me gloss over mu for now, and I'll explain what mu is right after. That's a very good question. So this is the basic point we're starting from, and so now we can ask ourselves, okay, how is this going to behave? And so we're going to look at some theorems and look at how we can compute it in practice, and then some demonstrations. But so before that, some of you may do game theory. And so there is like a game theory interpretation of this dissimilarity that we call diffie. So I'll be saying diffie from now on. So we have two players, and one player tries to find and challenge the other player with the hardest region in its own image, right? So the hardest region that we call H, that's denoted by H in the image F, and the other player, once it sees the image that was the region, sorry, that was chosen by player one, tries to match this region with another region that's in its own image, right? So I said the word image a lot. Let's look at what happens in practice. So if Ben is player one and I'm player two, maybe he chooses this highlighter first, this pink highlighter. Well, I can easily match that image in the right part of the, on the right image. If he chooses a mix between the black cap and the green cap, I can also do it. However, you can see that my function that I have to use, this blue circle, is maybe has a higher norm. And so I'm going to, the distance between the two images will be larger at that point, right? Then here, what happens if he takes the red pen? You can see that the red pen is not in the right image. And so I have to do my best to match the statistics. So to try to get some red, something close to red in RGB space. So maybe I take orange, and there's also some white, so I have to go grab the white cap. And so you see that here we're going to be very far. And so he's found a region that I can't match on my side. And so the images are far apart. They're not diffeomorphic one to the other, right? Whereas in L2 distance, they would have been close because the background is exactly the same, because I took this picture, it's a scene that I invented. And so maybe there's some overlap between the pens, and so the L2 distance won't be that large. So back to sort of the examples I showed before. So now we can sort of formalize it. So on the top row, you have 3 F images. On the bottom, you have 3 matching G images. And so the goal is to match the region that's in the blue dotted circle to a region in the G image, right? And so what is mu? Ruben was asking. So mu is something that helps us focus, because as you saw in the example right before, if there's an object in the scene that is not in the G scene, so for example, here the red pen is in the F image and not in the G image, well, the distance is going to be very far apart, even though maybe the rest of the image is actually a diffeomorphic transformation one of the other, okay? And so this mask that so that's denoted mu, allows us to focus on a certain region to avoid the occlusion, the problem of occlusion, which sort of trivializes the problem and makes it that every single image is not the transformation of another one, right? None of them are smooth transformations one of the other. So here we focus on this bottle opener and we try to find it in the second image. And so you can see what I've done is thresholded the H and Q functions. And so what you can see is that it doesn't select the background, right? It selects the object that has a rotation, a perspective difference, and then it matches it in with Q in the G image. So it's the same thing with the paw. It's going to match you see the claws, and then you see that there's a big difference, even though it's the same object, but it transforms this patch and sort of smoothly and transforms it into the fingers or the claws from another perspective. And so here on the Peppers image, so those who know MATLAB, Peppers is like a standard image in MATLAB for image processing, which is quite nice because there's a lot of objects that resemble one another. And so you can see here the pepper is rotated. There's a scale difference. There's slight warping as well. That's a synthetic example, whereas the other two are natural. You can see that it matches the same region twice. And so it does sort of grab the right transformation, okay? Okay, so I showed you, 3 examples. You could accuse me of cherry picking. You would be probably right. So the dream result would be that if I ask you the difference between F and F composed with Q, they're the same picture. So that's the dream. So we don't get exactly that, but we prove some results in that direction. So let's look at like a preliminary result. If G is the composition of F and of a smooth transformation, then if we remove any regularization, so we set lambda equal to 0, then we have an exact solution, right? And this exact solution is the change of variable formula, right? That we put with H and mu. So let me remind you the formula. It might be a bit small, but it's especially just to remind you that we're removing the regularization term that's right here. Okay, so there's no regularization. We can take Q to be in the RKHS, but to have as large as a norm as it wants. And so to be very irregular, maybe to grab several patches in an image to have a very large norm, right? And so in any case, we're always able to grab such a function, and it looks like this, right? As long as it belongs in the RKHS, but let's allow me to gloss over some of the technical details. So the proof is the change of variable formula, since Q is a diffeomorphism, so we can apply it, right? So we can achieve 0 for the first term, since we've killed the second term, given, let's call it Q0 star, okay, which is the optimal Q for lambda equals 0. So now let's look at the theorem we prove in the paper, which is, so under some expressivity and let's say functional hypotheses on the kernels, so that the spaces are rich enough and have some good stability properties that are algebras, things like that. For any regular diffeomorphism, we can prove the following result. For any function f, d lambda, so here we have lambda, we are regularizing, d lambda of f composed with q and of f, so the difference between the two images, is going to be bounded by 2 constants that depend on mu, so the mask. So this one is completely irrelevant to the images. It's just the shape of the mask, the norm of the mask, basically. And CQ, which is a constant that depends on the norm of the diffeomorphism Q that we choose, right? Or not that we choose, sorry, but that we observe, okay? And so then we can also give uniform bounds over a family of diffeomorphisms, if that's what you're interested in. There's an example in the paper. But so if we look at, for example, scale changes of a given magnitude, then we can sort of bound CQ and give an idea of what it looks like. And there's a third constant, which is lambda. And so what's important, and what you can remember, is that basically when we regularize, in the limit of small regularization, we get 0, which means that the bias that's induced by the regularization disappears when we use a small constant to regularize, right? Which is basically what we expect to see. And so So this means that when there's a diffeomorphism, in the limit of small regularization, the distance will be 0. And so the other direction is something we're working on now, which is more of an open problem. So which would be the converse, which would be if you have a distance, a diffeomorphism, if diff is 0, sorry, if d lambda of f and g is 0, can you say g is equal to f circle q? And that's an open question. So what does the proof look like? So it's actually quite simple. We apply the previous lemma, right? And so we know that since it's a min over q, the q0 star we had before, right? This quantity, the quantity that's achieved at that point, upper bounds d lambda, right? So we're upper bounded by the first term being 0, and then the lambda times the RKHS norm, right? The right term. And so if we fill it in, we replace it with q composed with big Q, mu composed with big Q, there's a typo, I'm sorry, h composed with big Q, and the Jacobian term, this norm is then what we have to bound. And so this, we can bound it using some classic properties of sub-Aleph function spaces. And so we bound this norm, and we show that when lambda, that we have this bound, and when lambda goes to 0, it goes to 0, okay? So that's the, let's say that's the guarantee we have on the behavior. And so here you can see that we have an optimization problem, but we haven't really talked about how we're going to solve it, right? There's a max, min, max, and I've been glossing over the fact that maybe at one point we'll have to solve it to get a value, and you've been trusting me, so thank you. And so let's see how we can compute it in practice. So actually we just have to take it one step at a time. So first, let's go from inside to outside, the inner optimization problem, and then progressively get out to the max over H. So the max over V, and so maybe certain people have taken a course on kernels, but the general idea is that this is a classic formula that defines the RKHS norm over F, so which is a functional norm. And so this is also basically the equality case for Cauchy-Schwarz, sorry. So it's algebra, please believe me. And then we're left with our min over Q. And so if we rewrite this, what we can notice is that in the norm, we have a transformation of Q. We take Q as an input, and it's linear. And so let's call the operator, the linear operator that we can define G, right? Like small g. And so this applies linearly to Q. Okay, and the same thing on the right. We take H in a linear fashion and we transform it. So it's the same. It's the same thing. So here, big phi I didn't mention is for those who are familiar with kernels, is the kernel feature map, right? That defines big F, right? And so defines the small v functions we had before. So here we've transformed our problem to a generalized least squared problem that we know how to solve, right? It's a problem in Q. It's like if you have least squared regression with matrices, and we can solve it in the same way. So that's what I just wrote below. And so let's solve it. And so we get something that looks like an eigenvalue problem now, because we have this operator T. I won't say what T is, it doesn't matter, but it's a function of G, Q, and F, right? And so we've transformed this max min max problem into a max min problem, right? Solving the first one. Now we've solved the second one, and now we have an eigenvalue problem. And so now, again, using operator algebra, this is the operator norm of T, right? And so T is this guy. So this is, if you're not familiar with operators, you can pretend it's matrices, and it's exactly the same thing. And so we get this closed form formula, right? So I said we wanted to compute it in practice. We found a closed form solution, but the closed form solution uses infinite dimensional operators between RKHS spaces. So we're not, we could be not quite happy with ourselves. And so we need to think about really computing it in practice. So we have a computational approach. And so let me describe it. The general idea is to say, well, we have operators, they're finite rank. And so a finite rank operator, we can represent it as a matrix. And so that's what we're going to do. We're going to, let's say, estimate the operators using finite matrices. So coming back to something we can put into NumPy, we're going to use the same formula. And then the operator norm in matrix space should give us a good estimate of the operator norm in, let's say, operator space, right? So the advantage of this is that we use randomized approximation algorithms that give us a good time complexity, because as you can see, so it depends on the dimension of X, the dimension of Y, which is 2 plus 3, right? So it's 5 when you have images, so it's a small constant. And then if big N is the number of pixels, because of course we've discretized the problem, if N is the number of pixels, the time complexity is in N to 3/2. So it's less than N squared, for example, even though we're comparing two images. Remember, we have two images with N pixels, and we have to do less, and we're doing less than quadratic. So it's actually low dimensional. And so the key behind this is, of course, of saying we're not going to look at images as n-dimensional objects, but as a function between low dimensional spaces that we then sample. So that's the key to this approach. And so okay, I said it generalizes well. It's cheap to compute, or it's cheaper to compute than what we could do naively. However, how good is it statistically? So as I said, we use random approximations using the Nystrom technique, or column subsampling. And so what we do, what we can show, using classic sort of concentration arguments, is that d lambda minus d hat lambda, so the distance between the approximation, is with high probability in 1 over square root of n. Okay, so this is sort of classic type convergence speed. So I've shown now that we can compute it in practice. Let's try to summarize and take a step back. So we got to this ugly formula, although it's actually quite elegant, but we got to this formula that's quite a mouthful, doing like an informal derivation, trying to think step by step how we could eliminate the problems that appear when we start from the change of variable formula. And so we got an intuitive dissimilarity that is small for data with small diffeomorphic perturbations. So that was sort of what we wanted at the beginning. So that's check mark. And the second thing is that we know how to compute it with using an approximation. And this approximation has the same behavior, because if we put together the theorem we had using Sobolev results and the approximation result using Nystrom, if we put them back to back, what we get is, with high probability, this inequality, right? So we have d lambda hat, the approximation that we know how to compute, is smaller than lambda, and then plus 1 over lambda square root of n, right? And this in n 3/2 time. And so what's left is to try to see it in action. What happens when we try to apply it? And as I said, this is leveraging really the power of kernels, which is seeing data as functions. And so since kernels work well in low dimensions, this allows us to leverage that. So a few examples. So these are examples that I built from a large image. I took a crop and then I rotated, scaled it, translated it a bit. And so remember also that there's a mask on F that's like a big circle that looks at the center of the image. And so the goal is to compare both of them and to see what happens. So here, as you can see, we have F on the left, G on the right, and in the middle, I overlay F with the H function that we find and the Q function that we find, or that the algorithm finds, right? And so what we can see is that the stem of the pepper is the one that's selected by the algorithm, and it's found when it's on the right and rotated, right? Same thing here with the small sort of green and orange pepper and the yellow one. You can see that it chooses the frontier between the two, and then this frontier is found again on the G image. And so here again, so it's actually the third one, not the fourth one, sorry. So you can see it grabs sort of the center with a few vegetables that are visible on the upper part of the image. And so this part ends up on the bottom right. And so you can see that it grabs it again, right? So what we can notice as well is that the values of diffie, the D of F and transform F, are quite small, of the order of magnitude of lambda. And so this is what we get, right? This is what we wanted. And so how about a negative example? Well, first of all, you can see that the value of D is much larger. Before we were at let's say 4 10 minus 2. Now we're at 8 10 minus 1. So we're quite larger and almost 2 orders of magnitude over lambda. Whereas the transformations are the same. So the constants haven't changed. Also, you can see that, so the two images do not look like one another. They're not diffeomorphic transformations. And what you can see is that it's going to grab something that's not in the right image. So for example, this garlic and the pepper, and it can't match the object, but it's going to match the color, right? It's going to grab some red and trying to match the statistics that it sees in the other patch. Okay. So how can we be a bit more, let's say, rigorous and say, well, okay, does the L2 distance, for example, the RMSE between F and G, the pixel-wise L2 distance, how does it behave? So let's take some random patches from the peppers image, and we can rotate them. And so what we get is the crosses and the X's, okay? So the X's are at the top. They're the values of the RMSE, and the pluses are the values of diffie, of the distance I presented. And so you can see that they don't have the same scale. So that's perfectly normal and expected. However, what's interesting is to compare it with random patches. So let's compare F and rotate F, right? The distance between the two with F and G, if F and G are random, which basically means, can we really tell the difference between some random patches and a patch and a rotated patch? Okay, so an example of rotation. And so what you can see is that the blue region at the top, the shaded region, is like sort of the random region for RMSE, right? You know, we know that we have good concentration results on RMSE, on the MSE, of course, but what you can see is that basically the crosses, the X's, fall in the shaded region. And so if I give you a pair of random images or a pair of images that are transformed to one or the other, then RMSE, the L2 distance, is going to give you basically the same value. So you won't be able to tell the difference between the two. On the contrary, the diffeomorphism invariant distance I have been presenting, in general is between 1 and 10 minus 2 in the red shaded region for random images. And when we take an image and its rotated counterpart, you can see that we're quite below it. And so we're significantly, let's say, quote unquote, significantly below, and we can tell the difference between them. Okay. So that's it. Let me just summarize a bit the results. So this is the definition. Although it looks scary, there's 3 maximization and minimization problems used to define it implicitly. So first of all, it works. It has sort of an intuitive explanation. We start from the change of variable formula, and then we patch it several times to make it work. And it's provably small when the diffeomorphic perturbations have a mild norm. So that's the first point. The second point, I'm repeating myself, is that we can approximate it efficiently. And so there's code online, actually. I'll show the link at the end. You can go and compare images that are warped to one of the other, or time series, for example, or things like that. And so we have, again, a good guarantee and a good time complexity of the computation. And so this is thanks to good use of kernels. And finally, the third point is that it behaves as expected on images, as you can see. So I showed you a small subset of the experiments we present in the paper, but so we presented sort of empirical evidence, theoretical evidence, and then some practical examples where we show what are the regions that the algorithm finds, that the problem finds, that show that the intuition we had does sort of go through the analysis that we did informally with hand waving at the beginning of the presentation. So thanks very much for your attention. I'm happy to take questions, and I can take the opportunity to say that I'll be at, so today I'm at the Turing, but I'll be at the AI Center as well this week and at Cumberland Lodge next week. So don't hesitate to come and chat.
All right. Good. Oh, good. Thanks very much. Do you guys have any questions? Please feel free to unmute yourselves.
Could you go over the part? Sorry, to the other person. Or was it just me?
Yeah, go ahead.
Okay, so could you go over that part again where it has the attention part? I think that's where I lost the trail of thought. So
Which part? Sorry?
where you focus, I think it was the mu.
Oh, okay, on mu. The mask. Yeah.
So how do we choose that?
Yeah, so we choose it to be, so you can choose it however you want. We choose it to be like, so this is like something that's, so let's go here, for example, something that's quite common in image processing to, like, for example, if you're doing Fourier transforms, which is not at all what we're doing, but it's something that, you know, let's say competing methods might use. Well, they always window the data so that you don't have artifacts linked to like the finite domain and the sampling in the Fourier transform. So that's like the first motivation, right? Is that you want to have like smooth objects. So we have a Blackman window that makes the object smooth at the border. So that's the first motivation. The second motivation is that, so here, these aren't, but let me go back to the end of my presentation. I had a synthetic example, not even synthetic, a fake example here. So if you're comparing the left images with the right images, if you give them to the dissimilarity on the top, it's going to tell you that they're not at all the same images, right? Because you have this green sun on the top left, and it's going to zoom in on that one. The H function is going to zoom in on that, and you won't be able to get anything green on the right side. You won't get the same shape. But the thing is that essentially they're the same images. And so the thing is that, okay, we're used to using square or rectangular images. So we're always going to have things in the corners that are going to bother us. And so we left open like a degree of freedom that you can add that is new. And so basically it's akin to blacking out, not pixel-wise, but it makes it not count in the distance what happens at the corners for the reference. So it really makes the left image like a reference, like a template. And so here we zoom in on the cloud, and so it's going to match the two images. It's going to say, yeah, there's the same thing on the corner of the other image. Does that answer your question?
Yeah, I think I don't know exactly how the mu zooms on it, but I get the idea.
So yeah, so it doesn't black out the pixels. So it's a bit misleading, but it weights the distance. Right, so you don't consider that the image is black at that point or another color, but you consider that. So my laptop is disconnected, but it's okay. You consider that it doesn't count in the distance computation.
Yeah, that makes sense.
Any other question, remark? You can see save those for Cumberland watch next week.
Yeah.
All right.
I think we are frozen kind of over here, but I don't think anybody else has any question. Do we have any more questions coming up, guys? Yeah.
I will have questions next week. I'll find you guys over lunch.
Okay.
Fantastic.
Very good. All right. Thanks.
Well, in that case, thank you so much, both of you.
Oh, I haven't done anything.
Yeah, your recommendation. It was fantastic having you here. So yeah, and we look forward to seeing you at Cumberland Lodge, I guess.
Yeah, thanks very much. Looking forward to seeing you as well.
Thank you.
Thanks, everyone.
Take care. Bye. See
Bye.
you.
Cheers.
Bye.
Bye.